Okay, good morning everyone. Today we want to look at the general tools of general theory of relativity, of course the basics you need in particular for tensor analysis that can help us cut through some of the things we shall be doing. Starting with some of the very simple operations that we perform in tensor analysis. For instance, here looking at the energy stress tensor from classical electrodynamics. We may want to, for instance, contract mu and nu. Of course, but then usually when you perform a contraction, one of the indices has to be a super, or should I say contravariant, and the other one has to be covariant. But you can see that both of them are all covariant. So we will want to perform an operation that raises one of the indices, and then we perform the subsequent contraction. Now I do that here now, hoping so we have, this is originally what we have over here, and this is mu alpha, and this is f sub alpha nu, and then I have here minus 1 all over 4. This is g sub mu nu. This is f alpha beta, and this here also is f alpha beta. Now at this point, what we could do is to use the metric tensor, of course. So for instance, I could do something like this: g rho. Let me raise the nu. G rho nu. See here, I have mu. And then what I will have in place there will be nu. Here also I'm going to have something like here, f mu here, I have alpha, then g again rho, then f alpha here, but then nu. So this is what we have. Of course, the usual thing is naively I can perform a sort of cancellation and then move the nu to take its former position. Now going here also minus 1 over 4 g sub rho nu, and then I have here with me g mu, but rho here. I have also f sub alpha beta, f alpha beta. Okay, now the idea is we have actually raised the index nu. So in the main expression, we can consider the index rho here to have taken the place of nu. So in a sense, what we will actually be doing will be performing a contraction between rho and mu. Remember we said you will have to raise the index before you're able to perform the contraction. And unless that is done, we can't. And so the only thing we can do now is to contract these two. So we will want to set rho to be equal to mu everywhere in the expression. And so what we'll have is going to be g mu, t here mu here, this is f mu alpha, and then this is going to be g rho, oh sorry, this should be nu, then this is going to be f, yeah, I had that to be alpha, and then I'm going to have here with me over here to be mu. So what I've done here actually is to a kind of, I think I might have placed this wrongly. So this alpha here is supposed to have appeared in a way. It's still alpha on top, but mine is just, I want to be able to keep track of how I lower it when I do. Okay, so that's what we have there. Now the next thing we can do is now looking at this one also, I have minus 1 over 4 g mu nu, g mu, and then f alpha beta, f alpha beta. Okay. Now the next thing I'll be looking at is looking at the whole expression. I'm going to perform 2 operations in the flow just for the essence of the space. Now I have here mu, I have here alpha mu, I have here nu alpha. So like I said, we had originally mu with us here, so it's the essence of my cleaning this initially to make sure that there are no confusions. So what I've done here is alpha is here, and then this is mu. So I'm going to sort of displace the indices in a way that is going to be clear for everyone to say. So for instance, I can move the mu's. I can move this alpha here to go up, and then this particular one here to go down. In other words, for instance, I have this, I can write this whole thing to be g mu nu, t mu nu, and then I have here with me f alpha comes down here, I can still maintain the G mu, although I won't have need for them anymore. alpha mu minus 1 over 4 g mu nu. And then I have here g mu f alpha beta f alpha beta. Okay, so that's just about it. So what I have here, you can see everywhere, I have g mu nu, g mu nu, g mu nu. That of course can be dropped. And now you can see I have left with me mu, and then I have alpha mu here, and exactly same thing, alpha beta, alpha beta. This of course dummy indices because they are all doubly repeated. And so in this case, for instance, g mu nu by the way, is equal to 4. So you can see in essence that what I have left from this expression is that T mu is equal to, here with me, alpha, f of alpha mu, f superscript alpha mu, then minus, like I said, g mu is equal to 4, the 4 cancels this. And so what I have here is f of alpha beta, and then here alpha beta. This of course is 0. Yeah, because I might as well change the mu's to beta. They are dummy indices, so those two terms there are the same. And of course that tells us that the energy stress tensor is stressless. Now this is just one operation that we could perform using tensor analysis. Okay, now so let's move on to the next thing that we have. The next thing we want to look at is a variation of what we do know to be the chronicle delta, written of course by a contraction of one of the indices of metric tensors. So if we have that this, of course, this is the general property, is equal to this, we could perform a variation that shows that the variation of this metric tensor in this form is equal to that. First of all, we can take a note, writing the original expression again, mu alpha g alpha nu to be equal to chronicle delta of mu nu. If I perform a variation of this, g mu alpha g alpha nu is equal to this. Of course, this is some constant, so the variation of that is 0. And the usual thing by Leibniz rule, you can say g mu alpha, and then this is g alpha nu plus g mu alpha, and this is going to give me g, let me make this all symmetric. This is going to be g alpha nu, and the whole thing is 0. So I could, for instance, say that this variation mu alpha multiplied by g subscript that is equal to the minus of g mu alpha, that g, and then I'm going to have alpha nu. Okay, so I would like to sort of multiply both sides from the right with some sort of inverse of this in order to let this stand all alone by itself. And then we can see if that corresponds to something like this. In order to do that, of course, I'm going to avoid any indices that is already contained in the tensor expression. So what I can do, for instance, is to say that this is d g mu alpha, g here, alpha nu. So I multiply both sides by something like this, rho sigma. Here I have minus g mu alpha, and then a variation of the g sub alpha nu. Then I have here with me rho sigma. Just so that it will be as it should be, of course, on both sides. Now looking at this, one thing I can try to do is to perform a contraction. Now I have to be very careful with some of the things I want to do here. So for instance, I can contract sigma and nu. I will of course have to do the same thing here. So if I were to contract sigma and nu, I'll be making the two equal. And if I did, what I'll be left with then will be something like this, a chronicle delta of rho alpha in this case. Now if I contracted sigma and nu, nowhere else in this expression do I get a thing like that. So for instance, in this case, all I'm going to have is going to be, for instance, minus g mu alpha, g sub alpha. So let me just give them with some expressions, say sigma. G rho here, sigma. So I've just made a contraction. Of course, I can't combine these two and say it's equal to some conical tensor because I have a variation of one of the G's here. However, on this left-hand side, I can decide to go ahead and say that what I have left for me is going to be, so I can use this conical tensor to change what I have already here. So this becomes G mu, but instead of alpha, I have that to be rho, so that disappears. Then I have here to be minus G mu, I have here with me alpha, then I have delta of G sub here alpha sigma G, I have here with me, I can say sigma rho if I like. Of course, it's commutative, it doesn't matter really how I place them, so nothing changes in that aspect. These are all dummy indices. So if I just want to make it look like what I have there already, it wouldn't be that much of a big deal because as you can see already from here, these two, the sigmas are dummy indices. So I can change them to whatever it is that I want. Of course, I have another one here, alpha, alpha. These also are dummy indices. But you can take note of a very important fact here, that the two indices here, mu, rho, were sort of splitted such that mu started here and rho was kept here. It's the same thing here, mu. So I have mu started here and then mu here. Now these alpha, alpha, beta, beta are dummy indices. So I have here with me alpha, alpha also, sigma, sigma, dummy indices. So we have in essence shown this. That is, of course, this is just what we're trying to show. So this is also one of the operations, and this is a very important formula that we'll be needing as you carry out any expressions or analysis using tensor analysis in general theory of relativity. Now we want to look at matrices, a very particular important property of matrices that we'll be needing. In general, in any matrix, you can define the inverse of a matrix to be this, where these are the matrices of the minors. Of course, when you multiply them with the corresponding sign, designation of each of those minors, you get what we call the cofactors. So when we divide